Good morning, everyone. Good morning from Radiocrafts. Good afternoon if you're from Asia, and I guess it's good night if you're calling in from the Americas. Welcome to this webinar. Today we're going to talk about range and reliability in RF networks, obviously, for smart metering and industrial applications. But just before we get into the core of that, just some housekeeping items. So next slide, please. So on the show today is myself, Anders Oldebeck. I'm the Sales and Marketing Director, but more importantly for the topics today is Ørjan Nottveit, our R&D Director, who will pick up the show here after I provide a few introductory words. Housekeeping today or this morning, we are scheduled for 30 minutes, and we will have, after the webinar, we will have a 10 to 15 minutes questions and afters. So post your questions in the chat window. We will answer as many as we can live during the 45 minutes we have here, and then if there's something remaining, we will make sure we respond over emails if there's something that requires some research, or if we don't have the time specifically. I would like to encourage you to introduce yourself in the chat window, then we know who's on the show, a little bit who you are and where you're from. That will help us to get a feel for who we're talking to, and also share your identity with the other people who is listening in. The questions, yes, I put that, so we'll talk about that. And also, we will put a recorded version of the webinar on our website after the show. So if you miss this, or if you have colleagues missing it, or if you would like to see it again, then just check in our website. We will put it up here in a few days after some edit. So call back in a week or so, and then it will be ready for you. Also, there will be a special offer for a development kit here after the show, so stay tuned. When we start the Q&A session, that offer will show up in the offer window in the webinar room. So with that, those few housekeeping items, let's get into the topic. So why range and reliability as a topic for a webinar here? Well, when I'm out talking to clients, engineers, customers, one of the questions I typically get is, what is the range? And my best answer, to be serious, it says it depends. I mean, if you're high enough over the atmosphere, you can probably send a signal to the moon with little effort. Or if you're in a room, which is the other end of the spectrum, if you're a room with stone or concrete walls, you can hardly send it anywhere. So range depends, and we will clarify a little bit why that is, and how you should treat range in a smart way. We would like to clarify a little bit how a network designer can understand how the radio equipment is specified, and then how it interacts with the environment, just to make sure to clarify the spec points that you see in the data sheet, and how to interpret them for a real-life environment. On reliability, it is a statistical measure. Any radio signal will have a risk of losing a packet. So the challenge for the engineer is, how do you minimize that risk? And we'll talk about what are techniques to do that, and what you should, as a designer, look for in terms of reliability, if that is one of your key care-abouts in your network. We have, Radiocraft, been working with defining standards, and we have been working on real professional equipment for the last 15 years. So we thought we would put together best of our experience and share that with you in this format today. But we also have some applications note and white papers on our website that you can look into. So hopefully this seminar will give you some practical answers, and hopefully will be of use for you when you design your own radio network. So with that short introduction, I'll leave the word for Ørjan and to dive into the technicalities of things. So Ørjan, over to you.
Thank you very much, Anders, for that introduction. So I'm Ørjan Nottveit. I'm the R&D Director at Radiocrafts, and I will be diving a bit more into the details here. First of all, this topic is kind of inspired by all the talk about low power wide area networks. So that has emerged as a new solution over the last, let's say, five years with the Sigfox and LoRa and all these other technologies. And basically, the theme nowadays is that you have one network ranging over the entire world, basically. So extended range is the differentiator of these networks. This presentation aims to educate the listener a bit on okay, why do we get these good ranges, because there are no really new technology behind any of these solutions. Why do we now have this new range, this high range? What has it cost in terms of reliability and also power? And the main focus is around Europe and ISM bands. However, it is kind of transferable to like 915 in the US as well. However, the discussions on 169 megahertz ISM band is, of course, that's only a European band, so that band is not an option in other parts of the world. Yeah, so range. This is a bit school background, actually, for those who are not recently out of school. Range is given by a couple of key factors, and this is the physics. You can't get around this. It's given by the radiated power from the different devices that transmit. It's given by the path loss. The path loss will be influenced by the height of the devices, the obstructions in the path, the frequency of your radio signals. We'll talk a bit more about that later. It's affected by external interference. It's affected by the gain of your receiver antenna and also by the sensitivity at the receiver end. So these are the parameters that physically will give you your range. And some of these you can influence and some you cannot influence. So the radiated output power is a key factor to get long range. So basically, it's the higher power, the longer range. It's as easy as that. And normally we say that 6 dB increase is double the range. That's like a rule of thumb, which is used in deployments of these networks. To bring that down to a different setting, it is that so there's actually an arrow there, because 10 milliwatt to 60 milliwatt is doubling the range. However, increasing the radiated output power will cost in terms of higher current. It will cost in terms of bigger batteries and naturally battery lifetime. So it is not a free thing to do. So you can do it to extend the range, but you don't really want to. Most often, the output power is also regulated, given by limited by regulations. For instance, in Europe, you have a limitation in 169 megahertz band of 500 milliwatt, which will influence the wireless M-bus at that frequency, or what we call the WISE Alliance, which is a alliance now pushing wireless M-bus based technology for 169. For the 863 to 870 megahertz band, which LoRaWAN operates in Europe, and also Sigfox operates in, it's typical 25 milliwatt. However, there is a small gap from 869 to 0.4 to 869.65, which is actually allowed to send 500 milliwatt. But neither Sigfox or LoRaWAN uses this from the devices to the concentrator. Output power can also be limited by battery, or that max current consumption that you want to have, the peak current consumption. And that is typically the case at 169, where you don't transmit the 500 milliwatt you can. You basically end up transmitting something like 50 to 100 milliwatt, simply because you don't want to pay the cost of the increased batteries. Path loss is often an interesting discussion. All of these technologies typically tells you about the free space path loss. That means the path loss if you send from where you are directly up to a balloon kilometers straight up above you. That's a very theoretical distance and not the distance you will get in any real application. So you can always end up with nice figures saying line of sight range of 50 kilometer, 100 kilometer, but these are just, for me, it's more theoretical figures than real data you can get in a real application. The height of the transmitter and receiver antenna is a key factor because it will influence the range a great deal. This is typically done by having a concentrator at a high spot, and that is something that all different technologies use, so it's not really a differentiator from many technologies. And also the device that is sending data, whether this is a meter, like a water meter, it could be underground actually, and or if it's some sort of sensors that gather data, you cannot really control where you put them because they are put somewhere based on the application. Also, obstacles in the way, like buildings and vegetation, you cannot control. Frequency you can control, and frequency is one of the things which actually gives you a benefit by going down in frequency. There are some references here that you can go into later to read a bit more about the background on this. Yeah, height of the transmitter is a key. So, but everybody who deploys big network knows this. So basically, they want to get the gateway or the concentrator side high up in a high building, and again, they cannot control the other device because that will depend on application. If it's a sensor measuring the number of cars which crosses a certain point in the road to measure and then report the number of cars per hour, that sensor has to be by the road. You cannot put it up in a, or it's very expensive to put it up in a high building. So frequency, I mentioned, it also influences the range. And that's basically, it can be seen from the free space path loss calculation. This is a standard formula that is known. And you see that the frequency is squared in the path loss. That means that the higher the frequency, the more path loss you have. And it's squared, so it accelerates even more. What this means in reality is that at 868 megahertz, for 2 kilometers, you have the same free space path loss as you have for 169 megahertz at 10 kilometers. So that's the difference physically. If you could look at it a different way, you can say that at 169 megahertz, you have 14 dB less path loss than 868 megahertz. In the same way, 868 will be much better than any 2.4 gigahertz radio. And this is why 2.4 gigahertz radio is really never used for these large area networks. Sensitivity is also a key factor. And here there is normally our trade-off versus the data rates. For instance, you have Sigfox in Europe operates according to their own promotion material at minus 142 dBm in Europe at sensitivity of the base stations, and minus 134 dBm in US and Australia. LoRa and the LoRaWAN, of course, has many different data rates. I've taken two of them here, which are relevant for comparison. Minus 137 is basically the chips given from the Semtech webpage, and minus 141 is found on a concentrator webpage. So I believe these to be kind of the area where they operate. 169 megahertz is operating typically at a higher data rate and not as good sensitivity as the others. So here's the drawback of that. They do operate at the 300 bit per second at minus 129 dBm. So they have like 8 to 10 dB less sensitivity, but they gained 14 dB in the free space path loss. So that pretty much, or not, that evens out a bit. We also have the higher data rate used by the wireless MBUS or device alliance, typically at 2.4 kilobit, which has a sensitivity expected on the base station at minus 124 dBm. Just to summarize the range thing, what we do get when you compare these three different technologies is that they have the different pros and the different cons. Some has less path loss, some has higher output power, some has better sensitivity. But what it ends up with is that these Sigfox, LoRaWAN, and WISE 106 nanomegahertz basically has the same theoretical range on all three of them. So it's more other things around them which dictates which solutions to prefer. But in terms of range, they're equal, pretty much equal. But range is just one part of this, I think, because reliability is a more important part for the end user. And what is reliability in this case? It's the probability of a packet being lost or actually being received. It has to do with the received power versus the internal noise floor. It has it is influenced by the signal fading during a packet. It's influenced by external noise, which again is influenced by the width of the channel, the time the packet takes on air, and the background noise. So I'll go a bit more into these factors now. This is for me a very key slide, because in terms of interference, there's three different things to consider. And if you talk to the marketing people at these different technologies, they would want to talk about one of these, not all three. Because to be disturbed by interference, the interference has to hit you in the time window you're transmitting. So if your packet take 1 millisecond, the interference has to hit exactly that 1 millisecond. However, if your packet take 1 second on air, then that means that the interference has to hit a 1 second window, which is a much higher probability. Also for the frequency domain, if you have a very narrowband system, that means that the interferer has to hit exactly the frequency that you're operating on. And if you have a wideband system with a wide receiver, it means that it's much more probable that the interferers will hit your frequency area. And also for the signal domain, the signal has to be a certain signal strength in order to interfere with what you with your packet. So let's talk about the signal domain a bit first. The signal domain is how strong the RF signal has to be to interfere with you, and this is what the LoRa people loves to talk about, because LoRa can receive with a negative signal to noise ratio because of their spread spectrum technology, and that's very, very nice. So that means that they can receive the packet with a stronger interference. However, if you go to the frequency domain, that's what the Sigfox and the wireless MBUS people like to talk about, because the LoRaWAN typically operate at a 250 kilohertz wide channel, while Sigfox and wireless MBUS has a much more narrow channel. So that means they have a receive filter, which filters away a lot of the noise, which are actually let into a LoRa channel. So both these technologies are narrowband, and that gives them an advantage in the frequency domain. So the time domain is something that none of these like to talk about, and that is the fact that they send very long packets. So, for instance, Sigfox, when you send a 12-byte application packet, they send 3 times 500 millisecond long transmission. So that's 1.5 seconds they transmit. Again, that makes the probability of being interfered much greater. device of wireless M-Bus at 2.4 gigahertz. That's they use a higher data rate, 2,400 bits. So that means that they make the packet much shorter in time. So they send the time over about 150 milliseconds. It depends. There are different options there, so it depends on the options. If you look at LoRaWAN with a 12-byte application packet and operating at 293 bit per second, and looking, giving in the overhead, which is specified in LoRaWAN, you see that it's about 1,450 milliseconds. So that's also a very long packet. So that means when you send a long packet, it's much more probable that something happened in that time window. Imagine you have a sensor by the road, and a car drives by, and that means that the signal actually drops for like a period of 500 milliseconds. That is much more probable that time window hits your packet when you send so long packets. And also the noise in the RF domain is not a constant thing. A lot of the statistical analysis on these different radio technology are based on the noise is being like a Gaussian white noise in the background. But study has shown that this is a study which I refer to here, which is done in Germany, where they measured the noise at both 868, 423, and 169 megahertz. They analyzed the noise, how it was packet oriented because of all others transmitting in this band. And they have shown that the average distance between interference packet is like 400 to 1100 milliseconds. So that means short packets are much more likely to get through the noise-free areas, while the long packets are more likely to be hit by this packet-oriented noise. And then I stole a figure from the same presentation here, which showed that they had a reference packet, and they saw that the probability of the packet being of collision with the packet based on the length of the packet. And here you see these are up to 300 milliseconds long, and you see the probability in this case of being hit was pretty high in their case. So the different technologies have different strengths. Some are good in terms of the signal domain. Some are good in terms of the frequency domain, that they are very narrow band and filter a lot of noise away. But all these technologies send very long packets, so they're pretty vulnerable in the time domain, all of them. So what can be done to increase reliability? What's normally done in a wireless system? Well, the most common thing is to use acknowledgement on the packet and retransmission. You can also have repeated packets. You can have a forward error correction coding. You can have a frequency hopping. These are all mechanisms to increase the reliability of a link. So repeated message, basically sending the same message multiple times. Sigfox send each packet 3 times just to get higher reliability. In wireless M-Bus, there is a redundancy in terms of sending the same metering data in several packets along the day. So you also have a redundancy in that system. Forward error correction is used in the LoRaWAN to get the better reliability. They use a 4 out of 5 error coding, which means they can handle some bit errors within the packet. But it also is part of what giving the long packet because of the overhead. ACK and retries. If you look at any other wireless technology on short range, this is what they all use. So this is, for me, the normal and best way to increase reliability. You get an acknowledgement if the packet is received, and you retransmit maybe 1, 2, 10 times. And that gives a significant better reliability. And you also will get a notification in case the packet is not received. So your application can change its behavior based on this. This is a challenge in all of these networks mentioned above. One of the reasons is that the gateway support many devices. And the gateway also has to comply to regulation. So there is a limitation on how much the gateway can transmit. At 169, this is 10%. So that means the gateway can only transmit 10% of the time, because otherwise it will violate with EU regulation. In Sigfox and LoRaWAN, this percentage is 1% or actually down to 0.1% in some of the regions. So that means you cannot acknowledge all packets simply because of regulation. A second reason is that all of these gateways that used for these technologies are half duplex. That means that when you transmit, you don't receive at the same time, or you get significant less sensitivity. So that means in order to receive the message from all devices, you don't want to acknowledge. So that means none of these LPWAN technologies have the reliability you get with an ACT and retries. So the conclusion, the conclusion is that, for me, is that one solution doesn't fit all. That means that there isn't one technology that will rule the world. There are all of these technology mentioned has their good sides, and all of them has their weaknesses. So there is not one solution that fits all, but all of these LPWAN technologies in the ISM band are vulnerable to interference, and a lot of them has to do with the long packets, and either they are vulnerable in the frequency domain and also in this or the signal domain as well. So that means that the application that uses this should be application which can lose 10% of the packets or lose 15% of the packets, because you cannot make a good business case of anything which needs like 99.5% reliability or anything based on any of these technologies. That also means that you cannot get a quality of service which is good, which is also a challenge. So again, this low power is good for application that can live with low data rates, and low, I wouldn't say low reliability, but not the best reliability. And they also have, because of this large packets they send, they also use significant amount of energy. So they're not really super. They all say they're low power, but the low power is based on transmitting 5 to 10 times a day. In case you have an application which needs to send packets each 2 minutes or anything, none of these technologies are really low power. So that means that for solution which requires more reliability, higher data rate, and lower power per bytes or per application byte you send, that means you require a technology which has smaller cells and fewer devices, and an LPWAN technology doesn't really fit this. So that means there are a need for other technologies as well. Again, going back to one solution doesn't fit all. There is a requirement for other technologies, and one of the solutions Radiocrafts is working on is a solution based on 802.15.4G, which is aiming at this, let's just say, medium range, low power, high reliability type of application. With that, I see that we have used now the 30 minutes, so I will go over to the Q&A session. So maybe Anders, will you go through this? I haven't looked at the chat while I was presenting, so maybe you would go through them.
Yes, absolutely. Thank you, Ørjan. I've been monitoring the chat window here, and so far I see a lot of people introducing themselves, but I haven't seen any questions coming in. So while our audience are thinking about that, and if there's something unclear there, maybe you can talk a little bit about one aspect of range that I don't think you covered in the presentation, which is how to get down in manholes. What are the differences between the frequencies as sort of seeing around corners, etc., which also influences the practical range of a wireless LAN or sort of an RF network.
Yes, of course. When it comes to going penetration through like concrete buildings and also bending around buildings, we also see that there is an advantage of a lower frequency over higher frequency. So that means that when I said that all these technologies are equal, that is in a free space type of area. So there is, though, advantage of a lower frequency like 169 when going through obstacles like inside buildings and through concrete walls.
Okay, thanks. And I see now some questions coming in here. So one is from Dzong, and question is about the output power. Does the regulator only set the max power, like 500 milliwatts for 169? And then can the user decide on the exact output power to use for the application?
Yes, and that's correct. The regulator for Europe, for instance, says that 500 milliwatt is the max. It's the same for 169, and for like 868 megahertz, the maximum is 14 dBm or 25 milliwatt. So that's the maximum, and that means when you go into the certification test, you have to be below that, simply. And then of course, but as I mentioned, 500 milliwatts at 169 megahertz will require radiated wise. It will require a lot of peak current. So that means that if you really try to radiate 500 milliwatts, that means it will be a very costly device. So that means normally this is set to something like 50 to 100 milliwatt for the 169 megahertz case.
Okay, thank you. Rutger is coming in with a question here about, can you tell more about the technology that we're working on, and that you, I guess this refers to your comment at the very end of the presentation. So can you talk a little bit about the benefits and challenges with 802.15.4G, which is the base for what we're working on?
Yes, so of course the 802.15.4G and E is kind of a standards out there, which has been there for a couple of years, which is the standard for sub-1 gigahertz communication. It's a star network in the basis, and it has built-in functionality which is common to what you see on 2.4 gigahertz and Zigbee. Means that it has things like ACK and retransmission and encryption and stuff on the lower level signals, and we also add more encryption security on top of it, and also try to format the data in terms of like say internet-friendly objects already at the sensors. So this is a technology which typically will cover the medium range, I would say. Because if you look at the very short range, that's dominated by, like, I don't know, 5 to 10 meters from you, that whole area is very dominated by Bluetooth Low Energy. And if you look at the same range, like 10, 15 meters indoors, you have these other technologies at 2.4, like Thread and Zigbee, which is doing a lot of work there. And then you have the low power area, which is then covering kilometers. But in some cases, you have things like a factory. You need to cover 100-meter indoor, but through a couple of walls. That means 2.4 gigahertz really won't do the work. You need to go to sub-1 gigahertz to get the range. And in addition, going through to low power wide area network is a possibility. But that means that you're limited to this unreliable system with no really acknowledgement and stuff. So that's that's what we aim for.
Okay. All right. Thank you. There are more questions coming in here. So from Marcel, how strong is the effective range depending on the noise introduced by the power supply of the wireless device? And what would you recommend in terms of the power supply? So I guess the question is how much problem is injected by the power supply in the system?
Yeah, this is a very practical oriented question, and it seems like Marcel has done these designs before because it is a relevant thing. Of course, when you have these really high sensitivity systems, that means that any noise generated inside your product is very will limit your sensitivity. So it's very important to have a good isolated power supply so it doesn't generate noise but not only from DC-DC power supplies, which they are typically noisy, but also for processor systems and stuff like that. If you have a processor system that can operating many hundred megahertz, that will also generate noise. So but this is typically handled in a concentrator, which has to have this fantastic sensitivity, at least for low power WAN. So that means, and they are often dedicated teams that do this type of concentrator. But yes, it is a key element of your design to make sure to isolate the receiver from any external noise or any internal noise from DC-DC or processors.
Okay, thank you. I have another question here from Jeff, which we can maybe give a general answer on. So his question is, if you have a system to support 2,000 nodes and each one is checking in once per hour, and we have a campus of, say, 2 kilometers across many low-level buildings, what would you recommend?
Yeah, it's difficult to answer that in a short time. I think I need to analyze it a bit better because it also depends on how large each packet is, how much data are you transmitting each time. Do you require do you need to get, what type of reliability do you need? Do you need to have 99.5% of the packets, or can you live with 90% of the packets and these kind of things? So it's difficult to answer, but so it needs a bit more detailed analysis.
Okay, so I fill in with my more sales pragmatic position here is that we see a lot of installations in the 169 megahertz area for meter reading. That covers this type of number of nodes and also the areas that you're referring to here. But that is for meter reading specifically, so that might give you some ideas there, Jeff. We have another question here from Mike. So power loss on connection. In one of the applications, he found a coax from the PCB near to the radio module. However, when I converted to using the MMXC connector, this is a new word for me, okay? Connector, and the range dropped to the point where I had to increase transmit power from 125 milliwatts to 160 milliwatts. Is this to be expected or something wrong? Very detailed question on that.
Yeah, so it was a very detailed question. Of course, in a single RF path, that means you must be careful not to have impedance changes because that will give you loss in terms of reflection. So it has to do with the layout of the MMCX and also the impedance that you see along the path in the cable and also on your PCB. So it is this is RF. You have to be careful with RF design basically to make sure that you have a good RF path from your transmitter to your antenna. And I would expect this to be reflection loss based on maybe the layout of the MMCX has a large capacitance to ground, which that would be my idea to look at that part.
Okay. Yeah, Mike, let us know if you have more detailed questions, and maybe if you can mail us, then we can go down to the specifics or your specific problem.
Yeah.
Nabil has a question here. Can you talk more about the quality of the RF chip in the concentrator, the role that plays in the range?
Yes. Again, the concentrators are normally built by either it's the LoRa or the Sigfox or Wise and Wallace Embus is typically made by dedicated constructor firms, and they make typically, they don't use the RF chips low cost that you use in the end devices. They use some more expensive stuff. That means they have maybe a software defined front end there. Maybe they typically use LNAs. They have more filtering. So it is more high end stuff that is needed in order to get these good sensitivities. And also, as mentioned below, you have to be careful at these constructors, because they typically have a large system, maybe a Linux computer or something inside, which generates a lot of noise. So they have to be very careful also to separate the receiver part from the processor and power part, in order to make sure that they don't get any noise in the receiver. So again, this is they have to have good RF knowledge. Yeah.
Okay, thanks, Ørjan. We are running out of questions here, so I think with that we will conclude the webinar. I'd like to thank everyone for listening in to our presentation, and just to remind you that this webinar will be is recorded and will be then put on our web for you to look at again, and maybe share with colleagues and friends. So, Ørjan, any final words from your side?
No, I would just like to thank everybody who came and listened, and wish them a good day.
Okay, all right. So thanks a lot, guys, and have a wonderful day. Bye-bye.